review of other functions. So that's where we have operations for addition, subtraction, multiplication, division, and then composition of functions. This is just continuing on from that transformations handout. This is the second part of it. So given the functions f of x equals 3 minus 2x and g of x equals x plus 1, determine the equation of h of x. Sketch the graph of h of x and state the domain and range of h of x for each of the next 4 questions. So what we have to keep in mind is that whenever we're adding, subtracting, multiplying, dividing the composition of functions, if there's any restriction on any of the functions that we're dealing with, that restriction restricts the whole way through, even if it goes away. So like if we square a square root, the square root was still there at some point, so there's going to be a restriction on the variable under the square root, which we'll see later on. So here we're going to do h of x equals f of x plus g of x. So what we could do is we could draw out f of x separately, draw out g of x separately, and then look at their y values for each separate x and add them. But instead we're going to actually just add the functions. So h of x equals f of x, which is 3 minus 2x, plus g of x, which is x plus 1. Plus signs are nice because you don't have to remember to distribute the negatives through like subtraction. So I'm going to get negative 2x plus x, which is negative x, positive 3 plus 1, which is positive 4. So I have h of x equals negative x plus 4. So I go to my y-intercept of 4. Kind of hard to see this. And then I'm going to go down 1, right 1, down 1, right 1, down 1, right 1. And if I wanted to go in the opposite direction, I could. I just have to do the complete opposite. So up 1, left 1, up 1, left 1, up 1, left 1. And then I connect them, and I have h of x. Now, 2 linear lines added results in a linear line. So my domain is still XER. This is in set notation, or in interval notation, negative infinity, positive infinity. And my range is YER, or in set notation, negative, or interval notation, negative infinity, positive infinity. Set notation is one with little squiggly brackets because it means the set of. Now our next one is h of x equals f of x times g of x. So we're going to do h of x equals f of x, which is 3 minus 2x, times g of x, which is x plus 1. Remember closed dots? There could be a closed dot between here too. Closed dots mean multiplication. Open dots mean composition. So I'm going to FOIL it out, and I'm going to get 3x plus 3 minus 2x squared minus 2x. I get negative 2x squared plus x plus 3. And that's my h of x. So we're going to type into our calculator to get our min, max, and x-intercepts, or we could do a whole bunch of actual work by completing the square or factoring to get our x-intercepts. We're going to use our calculator. You could type this version into your calculator, right here without the brackets, with the brackets, non-reduced form, and it will get you the same answer as this one. But if they want the equation, they most often want you to FOIL it out and collect like terms, more so what they're going to be looking for. Okay, so type into our calculator. Type in the original bracket form. So I'm going to go bracket 3 minus 2x, and then x plus 1. And in my red color, I'm going to put in negative 2, negative 2x squared plus x plus 3. Now, if you don't have the color one, where like I'm going to have one graph that's going to be blue and one graph that's going to be red, remember you can always arrow over to that line over here and hit enter once and it'll make it thicker for you. That's all you have if you don't have the colored functions. So now we're going to see if I did that math right. Oh, drew it right on top of each other, so that's perfect. You're trying to find the max, so second trace, which is calculate, maximum, which is 4, left bound of the max, enter, right bound of the max, enter, enter, and I get a maximum 0.2500013 and 3.125. Now, if I want to actually state those as fractions, I can see if they can turn into a fraction. Let's see if I can remind you how to do that. So you're going to go X onto your main screen and hit enter, and then you're going to go math, enter, enter. That one doesn't turn into a fraction. The Y is alpha 1, and then math, enter, enter. That one does turn to a fraction 25/8. So you could use fractions if you wanted to. However, I need more information. I need the x-intercepts as well. So I'm going to do second trace number 2, zeros. I'm going to go left bound of this one, enter right bound of this one, enter, enter, and I get -1, 0. And then I'm going to go second trace 2. I'm going to go left bound, enter right bound, enter, enter, and I'm going to get 1.5 and 0. So now I can at least sketch it. I might want to pull off a few extra points. I'm going to go second graph to the table of values and pull a few more points off of those graphs. So I like 0 and 3 for my y-intercept. I like 1 and 2, -2, -7, some more values just so that I can put a few more points on my graph. I'm going to go to my graph and I'm going to plot these. So my maximum is at 0.25 and 3.125. Lines on here. Wow, those are not straight at all. Okay. Your notes have it at least printed on it. This just didn't print very well. Okay. So I have 0.25 and 3.125, so close to here. And I have an x-intercept at -1, 0, and 1.5 and 0. And then I have another point at 0 and 3. I have another point at -2, -7. And then I have another point at 1 and 2. So sketch those. I have my graph. Now my domain is XER for set notation, or -infinity, +infinity for interval. And my range is y such that y is less than or equal to 3.125, or the fraction we found, YER, or -infinity to 3.125, square bracket, equal to. Right. Then we have division. So we need to do G divided by F, and G is x plus 1, and F is 3 minus 2x, so it's rational, a rational graph. Nothing cancels, so I have a horizontal asymptote and a vertical asymptote and no points of discontinuity. I have a vertical asymptote when my denominator equals 0, so 3 minus 2x equals 0. -2x equals -3, divided by -2, x equals 3/2. So at 1.5, So at 1.5, I have a vertical asymptote. And remember, wherever this function has x-intercepts, you're going to get a vertical asymptote. Remember, because that's where my denominator is going to be equal to 0. And then I have a vertical asymptote, or sorry, a horizontal asymptote at a fraction of the coefficients because it's the exact same degree. So y equals negative a half. I can go to my calculator and plug it in and then pull some values off my table of values. So I have negative 1 and 0. I have negative 2 and negative point something, getting closer to that negative a half. Then if I go to 0, I'm at 0.3. 1, I'm at 2. And then it just goes up something like this. Backward. At 2, I'm at negative 3. At 3, I'm at negative 1.33. At 4, I'm at negative 1. At 5, I'm at negative 8.57. I keep getting closer. So I'm going to run along here, curve up here, and then run along here. Rational functions domain and range is really easy. It's just what the asymptotes can't be. So in this case, it can be x such that x cannot equal 3 halves. XER. It equals everything else. So I just say x cannot equal 3 halves, and then I follow with all the x, and x is an element of all the real numbers. So all the real numbers that are not 3 halves. And then I'm going to do y such that y cannot equal negative a half. If I wanted to show that one in set notation, I'd have to go negative infinity to negative a half round bracket, or a half, negative a half round bracket to infinity, just showing that it doesn't equal that. And then my last one is a composition. So it's G composed of F. So for every X, everything in F, I'm going to put in every X in G. I have H of X equals G of F. F is 3 minus 2x. And now I'm going to put this in for every x in G. So H of x equals G, which is x plus 1. So instead of an x plus 1, I'm going to now have 3 minus 2x in for x plus 1. So I get negative 2x plus 4. I'm going to draw that. Okay. So I go to 4 on my y-intercept, and then I go down to right 1, down to right 1, or up to left 1. So it's negative 2x plus 4 in simplified form, and then negative infinity to infinity, or XER, YER. Okay, so that's if you have functions. If you have equations, you can actually just do the operations to the equation and then graph that equation, keeping in mind that if any of the equations along the time have a restriction, you have to hold that restriction through the whole time, not just hold it till it goes away. And that will come be explained more later. Now, you can only compare graphs where both graphs exist. Both of these graphs exist between x's 0 and 4. If one of them existed between 0 and 4 and one of them existed from negative infinity to positive infinity, we would still only be able to compare these graphs and do operations between 0 and 4. So here it says the graph of y equals f of x and g of x are shown. They want f of x plus g of x. So we can actually go all the way from 0 to 4 on both graphs here. Find our x's at those values, take our y's and add them. Find our x's and then take the y's and add them. Okay? Like I said though, if you had a graph, one graph that was like infinity, and one graph, the second graph was like this, I would only be able to do operations on 0 and greater. All right, so we're going to look at the zeros first. We're going to make ourselves a little table if we want. So we have f of x, we have g of x, and then we're going to have h of x, which is those two added. And h of x, f of x, g of x, that all just stands for y's. We've been told that since we were young. It stands for y's, but different y's on different graphs. That's why we have f and g and x and h and all those stuff instead of just a y equals. So at 0, I'll put an x column here. At 0, our f is 2. Our g is 0. I add them, 2 plus 0, and I get 2. So my new graph is going to be at 0 and 2. Then I look at 1, f of x, my y is 3, g of x, my y is 1, and I add them and I get 4. So my new point's at 1 and 4. Okay, I'm going to circle these ones. So this is my new coordinates, 0 and 2, 1 and 4. Okay, my next one, I look at 2. 2 for f is 4. At 2, my g is 2. And then I'm going to go 4 plus 2, which is 6. And so my new point is at 2 and 6. Then I have 3. 3, I'm at 4 on the f. On the g, at 3, my y is 1. So 4 plus 1 is 5. So my new point is 3, 5. And then at 4, I'm at 4 on the f. And at 4, I'm back at 0 on the g. 4 plus 0 is 4. That's my new point, 4, 4. And that's my new graph of f of x plus g of x. So you literally just take the same x's, find the y's for those values, and then do the operation, whether it's multiplication, division, addition, subtraction. Yeah, that's all you do. And then you have your new graph. And remember, like I said before, you can only compare. So if I have this line graph here on the side, and I have this radical graph here, I would only be able to actually do operations on the graphs this way. Nothing over here because I have nothing to add to it, or subtract or divide or multiply. All right. Division 1, and I like the division ones because those are the ones that everyone forgets about. Okay, so I'm going to put some lines on this graph. I wish the lines actually worked. If it didn't, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so same thing. I'll show you a different division one as well, one where it crosses the x-axis because that makes a big difference. But we're going to go here. This is hard to tell. These are at 2's. So at -2, I'm doing f divided by g. This is f, this is g. So I have to do it in the correct order. So I'm going to do 4. At -2, I'm going to do 4 divided by 4. So now my new point, 4 divided by 4 is 1. So I'm going to have negative 2 and 1 as my new coordinate. Then I'm going to do 4 for negative, so that was negative 2. Then I'm going to do it negative 1. 4 divided by 4 again, which is 1. I'm at negative 1 and 1. Then I go to 0. 4 divided by 4, which is 1 again. So I'm at 0 and 1. Then I'm going to do 1, 2. Okay. Then I'm going to do 4 for 1 and 4 and 2. 4 divided by 2 is 2. So I'm at 1 and 2. Then I go to 2. I'm at 4 and I'm back at 2. 4 divided by 2 is 2. And then I'm going to go to 3 and I'm at 3. 3 divided by 2 is 1.5. Then the last one, oh, more. 4 is 2 divided by 2, which is 1. And then 5 is 2 divided by 4, which is a half. That's my new graph. Now, let's do a little tiny graph here. Say this is F. Do a small little graph. That's my f of x graph. Remember, I can only compare same domains where they all exist on both graphs. So negative 2 here, 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 and back here. Okay, this is g of x. And I want to graph f of x divided by g of x. So basically, wherever this is equal to 0, I'm going to get undefined, which is an asymptote. Wherever f of x, the numerator, is equal to 0, I'm going to get 0 divided by something, which is just 0. So it's only our denominator that's an issue. So let's go through here and we'll make a little table and graph. Okay, so this is going to be f of x divided by g of x. Okay, so my first point here on f is negative 2 and negative 1. So I have to go to here, negative 2 and positive 1. So I have negative 2 f g f divided by g. This is my x. So my f at negative 2 is negative 1. My g at negative 2 is positive 1. So I'm going to do negative 1 divided by 1, which is negative 1. So my new coordinate is negative 2 and negative 1. Okay, then I'm going to look at negative 1 for my x. Negative 1 on my f is 0. Negative 1 on my g is 2. 0 divided by 2 is 0. Because whenever my f is 0, I'm going to end up with the 0 because it's 0 divided by something. So my new point is negative 1, 0. Then I go to 0. At 0 on the f, I'm 2. At 0 on the g, I'm 0. So I'm doing 2 divided by 0, which is actually undefined, or a vertical asymptote. So I have a vertical asymptote when x equals 0. And then I have 1. At 1, I have 0. At 1, I have negative 1. 0 divided by negative 1 is 0. So 1 and 0. And then at 2, I have negative 1 for f. I have 0 for g. I have negative 1 divided by 0, which is undefined, which is a vertical asymptote. 2. So I know I would have to pick a whole bunch more points in order to graph this, because these lines connect, but what do? Do they go up? Do they go down? What happens here, right? So if they give you this many, you'd have to pick more points in between to figure it out. But you could answer any questions now. They might ask you, where are vertical asymptotes? And you could tell them now at x equals 0 and 2. They ask you, where are the x-intercepts on the graph of f of x divided by g of x? And you could tell them now at x equals negative 1 and 1. So you can answer stuff from this, which is often what they do. Not making you graph it per se always all the time, but actually making you answer any question. So in your denominator, this g of x, when there has y's that are 0 on that graph, you're going to get asymptotes on your new graph. And where f of x has y's that are 0, you're going to get new x-intercepts. Okay, that's what I want you to take from this little sketch that I did. Okay, now these ones here, for the most part, have values instead of x's. So what do I have here? I can expand this. I'm going to do g of 3 plus h of 3. Whenever I don't have x's anymore and I have values like a number like 3, my answer to these questions is going to be a number. I have no x's left. Okay? So my answer is going to be numbers. So we're going to do 4 of 3 squared plus 2, because that's g of 3, plus h of 3, which is 3 times 3 minus 7. If you wanted to do g of 3 off to the side and h of 3 off to the side, then bring their values in and add them, you could absolutely do that. You wouldn't have to do it all together like I'm doing. So you'd go 4 times 3 squared, which is 4 times 9, which is 36, plus 2, plus 3 times 3, which is 9, minus 7, and that gets you 40. There's your answer. So g plus h of 3 here is 40. That would be your answer. This one is g of 5 divided by h of 5. So like I said, I could go off to the side and I could find g of 5 first. Okay, that's 4 times 5 squared plus 2, which is 102, because it's going to be 25 times 4 plus 2. And then h of 5 is 3 times 5 minus 7, which is 15 minus 7, which is 8. And I could come back here and I could say, oh, g of 5 is 102. I did that off to the side. H of 5 is 8. And that reduces to 51 over 4. So you could do it all in one step and show it together, or you could go off to the side and find them when they actually have values for x. So I'm going to do h of 10 off to the side. H of 10 equals 3 times 10 minus 7. So we're filling it into the 3x minus 7 equation. So I'm going to get 30 minus 7, which is 23. And now I'm going to fill that in for h of 10. So I'm going to get h of 23 now. H of 10 is 23. So now I'm finding h of 23, which is 3 times 23 minus 7, which is 62. I'm going to do g of 3 off to the side. So I fill into the g formula. 4 times 3 squared plus 2, which is 38. So now I know g of 3 equals 38, so I can fill in 38 for g of 3. And now I have to find h of 38. So I'm going to do 3 times 38 minus 7. I'm going to fill 38 for all the x's in h. And then 3 times 38 minus 7 is 107. H of 3 off to the side. That equals 3 times 3 minus 7, which is 9 minus 7, which is 2. And now I can fill 2 in for h of 3. So I'm going to do g of 2. g of 2 is 4 times 2 squared plus 2, which is 18. Then I have g of x plus h of x. There's nothing to fill in for these values, so I actually have to fill in the entire equation. G of x is 4x squared plus 2 plus h of x, which is 3x minus 7. If it was a subtraction sign, I'll go through that in a second. So plus doesn't matter. So I'm going to get 4x squared plus 3x minus 5. And I'm done. Please do not set it equal to 0 and solve. Okay? That's where you guys error here. You set it equal to 0 and solve. You are done. I just want to know what those two functions are added together. So once you've collected like terms, you are done. The only time you should get an answer of like 7 or 3 or 4 is if they give you a number to fill in for x. Okay? Now what if I did off to the side here, g of x minus h of x as like an f part 2, let's say, and this would be an f part 1. So g of x minus h of x. So I would get 4x equals 4x squared plus 2 minus 3x minus 7. And they'll have an error to this answer. Because what you have to remember is you have to subtract everything behind that subtraction sign. So you're going to get 4x squared plus 2 minus 3x plus 7. And so you get 4x squared minus 3x plus 9. You're done. This last one is composition, h of g of f of x. So first off to the side, I'm going to find g of f of x. And then when I figure out what that is, I'm going to put it into this spot and find h of it. Okay? So g of f of x means I take f and I plug it into all the x's in g. So g is 4x squared plus 2. So I'm going to go 4, and instead of x, I'm going to put an f, which is x minus 2. I'm going to square it plus 2. Now, before I square this answer, hey, I have a radical in my question. If I have a radical in my question, I have restrictions because what's underneath the radical sign cannot be negative. It can be 0, but it can't be negative. So I'm going to do a restriction. X minus 2 has to be greater than or equal to 0. X has to be greater than or equal to 2. Done. My domain is forever and always in this question going to be restricted to, at the very least, greater than or equal to 2. It could be restricted more if I ended up with like a rational expression in there or something else when I kept going doing compositions. But if at any point in time I have a radical or a restriction, whether that radical goes away by squaring it, which is going to happen soon, I still have a restriction on that radical. So that domain will always be restricted. So if I want to go type this into my calculator later and I wanted to see what my domain would be, like you guys did in your mock and got it wrong, please remember that you have to restrict your radical even if it goes away. Just like with rationals, you state the non-permissible values. Even if they cancel off, like a point of discontinuity, that x value still doesn't exist. Whether it goes away in cancellations, it still doesn't exist, and your domain would be x cannot equal that value. So I am going to simplify this now. So the radical and that is going to go away, but I still have the issue that back here when I did this question, I had a radical. So the domain is going to matter. Plus 2, and I get 4x minus 8 plus 2, and I get 4x minus 6. Great. That's what g of f of x is. I still had an issue back here, so my domain is still restricted like this. Even though this looks like a line, my domain is still restricted because back there was a radical, and the radical causes you to have restrictions because you cannot have negatives under the radical sign. So I now know that this 4x minus 6 is g of f of x, so I can replace it. So I'm going to get h of 4x minus 6, and I'm going to plug 4x minus 6 in for h. So I'm going to get 3 times 4x minus 6 minus 7. So I get 12x minus 18 minus 7 equals 12x minus 25. Done. Do not solve it. Do not find out what x equals. I do not care. I didn't ask you to solve. I asked you to simplify. Okay? So you're not solving. None of these would say solve. They would tell you to determine, but not solve. Okay? So here's the last page. Given that f of x plus g of x equals that, determine possible values for f of x and g of x. So you need to figure out f of x and g of x values that when you add them in collected like terms, you would get 4x squared minus 2x plus 5. So if I made, let's say, f of x have a 6x squared, I would then know that g of x would have to have a negative 2x squared, so that when I add them, I get 4x squared, which is my resultant. I'm going to make a negative 5x. Well, then I know my g is going to have to be positive 3x, so that when I add them, I get negative 2x as my resultant. And then I'm going to pick plus 15 for my f. Well, then my g is going to have minus 10, so that when I add them, I get 5. So there's so many different answers because I just picked something random and then picked a g that would balance out my f equation. So there's so many options, right? This one here is a little bit less options on how to make it easy. So I'm going to plug into g in for the x and f, right? So if I make f b, if I made g, let's say, be the hard part, make g of x be square root x minus 2. Then, before I replace it in there, it would have been an x, right? So therefore, my f of x would have had to be 2x plus 3. So if you make your g be the intricate part of the equation, then your f's really easy to come up with. Okay. And then our last one. So we have sketch the graph of g of f of x. Okay, so we're going to do g of f of x. F of x is 2x plus 4. I'm going to fill it into g. So I'm going to get negative 1/2 times 2x plus 4 plus 6. So I get negative x minus 2 plus 6, which equals negative x plus 4. And then I just graph that. So I go to positive 4, down 1 over 1, down 1 over 1, down 1 over 1, and I would have my line. That is a terrible line and very bothersome, so I'm going to try again. Okay, 4, down 1, over 1, down 1, over 1, down 1, over 1, down 1, over 1, down 1, over 1. Oh, goodness. There we go. It's a little better. And that would be my resultant. And that's it. So what you need to take from this, for the most part, that everyone forgets is that if there's a restricted domain at any point in time throughout your equation, it stays restricted even if it cancels off by a squared or some other reason. If there is a denominator, you have to look for your vertical asymptotes, okay? Also, if you are dividing functions, remember that whatever function, so I'm going to remind you of this, if I have f of x in the denominator this time and h of x in the numerator, let's say, wherever the heck f of x equals 0, which is the x-intercepts, I'm going to get vertical asymptotes on the graph of this combined function, the g of x graph. And wherever h of x equals 0, I'm going to get x-intercepts on the g of x graph, right? So this is vertical asymptotes, and this is going to be where I'm going to get x-intercepts. Okay? So you need to remember that, because they might ask questions like that.